How is a proton actually born? If we could watch it from inside the energy sea instead of just staring at three thin lines in a textbook diagram. In the energy filament theory, a proton is not three abstract points in a box. It is three tiny, unstable filament rings that discovered one special way to lock together so that the whole structure becomes far more stable than any one of them alone. In the previous episode, a single quark was a very small loop of filament with a straight tension pattern that leans hard to one side, like a thin rubber band pinched into a crooked little circle that wants to spring back the moment you relax your fingers. So a lone quark in the energy sea appears for a moment and then very quickly falls apart. To live longer than that blink, a quark has to find partners and use its own asymmetry to cancel the others. The way three weird puzzle pieces, each with jagged edges that look wrong on their own, can suddenly form a clean triangle when you rotate them just right and press them together. A proton is exactly that snapped together triangle, three quark rings, each dragging along a one-sided straight texture. Line up so that their textures connect tips to tips and form a closed loop of three tension bridges. Each bridge pulls on two rings at once and helps hold the third in place. So although each quark alone is unstable and wants out, the three together dropped into a lower cost, the last effort configuration that behaves like a tiny fortress sitting in the energy sea. You can picture the proton as a tent held up by three ropes. The fabric itself is soft, but three tight ropes pulling in different directions let the tent stand firmly on the ground. And if you try to cut or stretch one rope, the other to first go even tighter and the whole structure stiffens before anything breaks. The same thing happens if you try to drag one quark out of a proton. You do not gently loosen the connection. You stretch the three texture bridges straighter and tighter. The tension cost shoots up, and from the sea's point of view, it becomes absurdly expensive to let a bridge simply snap. The cheaper move is to roll up a brand new pair of tiny rings in the stretched region, a fresh quark-antiquark pair, and reconnect the bridges so that you end up with more bound combinations instead of a single free quark in empty space. The harder you pull, the more the system answers by making new pairs to heal itself, which is why high-energy experiments see jets of new particles rather than isolated quarks. This is what strong interaction and quark confinement look like here. Not glue or metal bars, but bridges that tighten as you separate them and a geometry that never rewards letting one quark escape alone. Now we can finally answer why the proton is positively charged. In this picture, electric charge is not an added sticker. It is a simple rule about how tightness is distributed. When the outer side of a filament structure is tighter and the inner side slightly looser, the energy sea reads it as positive charge. When the inside is tighter and the outside looser, it reads it as negative charge. Inside a proton, the three quark rings and their bridges pull in such a way that each tension bridge, like a rope on that tent, is tugging the outer region of the structure extra tight while the interior region ends up relatively relaxed by comparison. To the energy sea, the proton is a small domain that is tight on the outside and softer on the inside. And that tightness profile is exactly the visual meaning of +1 charge rather than a mysterious label. So strong force, quark confinement and the proton's positive charge stop being three separate riddles. They all come from the same underlying mechanism, where shape fixes how tension is shared, and the resulting tension pattern decides both how hard the structure is to pull apart and how it shows up electrically. In one plain sentence, a proton is born when three unstable quark rings with crooked tension patterns find the one way to point their asymmetries so that they lock into a tiny, extremely stable triangles, whose tightening bridges explain at the same time why the binding is strong, why quarks never fly out alone, and why the whole object carries a single unit of positive charge. Tap follow, share it on New Physics, Clear Universe.